This is joint work with Enrico Kravina, a bachelor student at ETH Zurich, and my PhD advisor, Thomas Gross. Enrico did a great job on the implementation, while I worked more on the original binary translator and the design phase. The motivation for this work started when we were debugging a very large application. Let's call it OpenOffice for now. And we were trying to look at all the memory accesses of that application and trying to check out to recover from specific memory bugs. And we found out that Valgrind just doesn't scale up to that task. And we were exhibiting something like 60x overhead. And the slowdown was just not doable for these large applications. So let's start with the motivation. We want to execute additional code for every single memory access that an application executes. And we call these little codes or code snippets memlets. And a memlet, in general, inspects one single memory access based on a specific set of features. So the features can be the target address of the memory read or memory write, the type of instruction that executed the memory access, or the prior state. Like there will be some shadow state in the background that the memlet can act upon. And memory tracing is one of these nice techniques that can be used for a whole bunch of different applications. For example, you can do very detailed memory logs for debugging purposes. You can do memory checking, you can do security checks, you can do data flow tracking, privacy extensions, and all these things. But the big requirement is that memory tracing should be very, very cheap. And in production, usually 30 or 60x overhead is just not tolerable. So the general technique of memory tracing uses some form of binary translation to weave these additional memlets into the executed code so that the memlets execute alongside with the already existing code. We present here memTrace as a general technique that supports any form of memlet, but for the sake of simplicity, during the talk, we'll focus on a specific memlet and specifically unlimited watchpoints. And watchpoint basically checks for every single memory access if a read or a write watchpoint is set for that specific location. And if it is set, then it traps into a debugger, a debugging process, or a general inspector that runs alongside the application. So let's look at the quick x86 example. We have a very small basic block that basically does an add long instruction, dereferences the EBX register, loads 4 bytes, and adds these 4 bytes to the EAX register. Depending on the outcome of that load, we jump to basic block 1 or basic block 2. So memory tracing takes that single memory access instruction and adds a whole bunch of additional checks on top of it. So it first calculates the target address, compares it to a specific value, and then if a specific condition is set, it jumps to a handler. And if you look at this abstract piece of code, additional code, we might already see several problems that we might run into if you use just regular binary translation. First of all, we needed additional registers for the memlets. And register reallocation in a binary translator might possibly lead to a high amount of additional overhead and comes with additional complexity in the binary translator itself. So this is the first problem we have to take care of. Another problem is, where do we place the shadow state? Can we just place it linearly somewhere in the address space of the application? Or do we have to add an additional layer of indirection in the virtual memory infrastructure, which will again cause a high amount of overhead? And there are a whole bunch of other design decisions that you have to take care of. And in addition, we execute a whole bunch of additional instructions for every single memory access. And this might cause additional overhead as well. So keeping these different problems in mind, we want to design a very efficient memory tracing infrastructure that is achievable with very low overhead. And key to lightweight memory tracing is that when looking at modern CPUs, we found out that for the last 6-7 years, most CPUs have been shipped with support for both 32-bit code and 64-bit code. And also in the ARM world, the CPUs support multiple different ISAs. And for example, modern Intel CPUs support both x86, the 32-bit version, and x64, the 64-bit version, while most programs still run in a 32-bit world. And I guess it's safely to assume that many programs will be content even in the future to run as 32-bit applications. And if you look at the current systems, most applications run on just 32-bit code. So we envision to use cross-ISA binary translation that allows the tracer, the tracing infrastructure, to use the additional hardware that is available in the larger target ISA. So on one hand, we have a wider address space to store all our additional tracking and tracing infrastructure in. And we also have additional registers that enable us to use simpler translation techniques and faster binary translation on top of it. So after motivation and introduction, the outline of the remainder of the talk is as follows. I will describe the framework for lightweight memory tracing that we built. I will discuss specific requirements that need to be fulfilled for this memory tracing infrastructure. We will have a look at 2 user-definable memlets. We'll look into details of cross-ISA binary translation, quickly discuss the implementation, evaluate the whole system to see if it actually runs faster as I promised, quickly discuss related work, and in the end I will conclude. So let's start right off with the tracing requirements that we have. First of all, as a user of such a tracing infrastructure, the thing you want most is flexibility. You don't want to be bogged down to a very limited set of registers that you can use, very limited state that you can use, and so on. So we want the user to be able to express their memlets very independently. So you can specify different access pattern based on memory accesses, access type, types of instructions, maybe if it is a floating point instruction, and so on. But we also want some other kind of flexibility. So the binary translator should support the full set of the source ISA. So we do not want to restrict the application in any form, for example, limiting the use of floating point instruction or anything like that. The second requirement that we have is isolation. So the binary translator should be isolated from the running application. And we want to enable the application to run in an unmodified memory space. So the 32-bit applications should run unmodified in a 32-bit, in the lower 4 gigabytes of memory. It should use its original registers. It should, as much as possible, adhere to the original timing constraints and so on. And we must still support all the additional memlets that run on top of it. And last but not least, the most important point is performance. All these additional code that we add to the executed application must be fast. So we must have both reasonable performance overhead and reasonable memory overhead. And we'll look at how we get down to that reasonable performance in more detail later. First of all, the flexibility that we want can be achieved through binary translation. But as I said in the motivation in the beginning, binary translation can come with a very high price tag if you have to do register reallocation and additional compilation and so on. It might result in a very high price tag. We use a simple table-based binary translator that translates from one ISA to a sibling ISA, kind of, in our prototype implementation from x86 to x64. And we take the unmodified original x86 code, run it through our dynamic binary translator, which translates on a basic block level and uses a simple table-based translation scheme. All the additional memlets that are defined by the user are woven directly into the translator code, into the basic block. So every memory access is instrumented by itself. The translator code is then placed in a code cache where it is executed. And we achieve, the dynamic binary translator ensures that most of the execution time is actually spent in the code cache, which only contains translated x64 code. On the hardware side, we only execute x64 code, and whenever we would jump back to the original x86 code, we fall back and trap into the translator and translate that basic block and ensure that all outgoing edges either point to already translated code or back to the dynamic binary translator. Using this approach ensures that all the memlets execute alongside the application, are woven into the application, but are again separate from the application because they use different hardware, and they use different sets of registers and different memory areas. The most important argument for isolation comes from the larger memory space. So if we run in a 64-bit memory space, we have a nice option to use a whole bunch of 4 gigabyte blocks that can be used for all additional stuff that we want to add. And we can keep the lower 4 gigabytes just for the application as it would run normally. So we map the lower 4 gigabytes and run the application as if it was accessing only the 4 gigabyte block at the bottom with all its code, its data, its heap, and its stack regions. For the individual memlets, we add a set of shadow memory blocks that are all 4 gigabytes on top of it. And the memlets then access the corresponding shadow areas to get their additional data on top of it. In this example, and for the unlimited watch points, we only need one additional 4 gigabyte block of shadow memory. For other memlets, let's say for dataflow tracking, you use a set of additional memory blocks. If you want to store, for example, 4 bytes for each byte in the original memory block, you store 4 gigabyte blocks, and you just concatenate it together. And you can write it in the memlet so that you can concatenate these 4 blocks. And last but not least, we have one additional block that contains the translator and the translator memory, with the code for the binary translator, the code cache, the translator data, and all the translator stacks and so on. And this ensures that through the wider memory space, we can isolate the tracer from the application itself and separate it. Keep in mind that the application just runs in its 32-bit memory space, and all the pointers inside the application will only be 32-bit pointers. So the application can never access the higher memory regions, and we can therefore easily separate it. While on the other hand, our memlets, our additional code, can access both the higher memory region and can also inspect the lower memory region of the application, and thereby modify these two things. Key to low overhead, first and foremost, is fast and efficient binary translation. And because we do not need to take care of register reallocation and a whole bunch of additional complex things, we can use a simple table-based mapping scheme where one instructions are basically decoded and directly mapped into the code cache. And we only need to take care of the indirect control flow jumps, control flow transfers in addition to that. So we can use a very simple and efficient table-based binary translation scheme, and we do not need to lift the machine code into a high-level IR like Valgrind does and then compile it back down. This already gives us a speed advantage for vanilla binary translation. And the second part of the key features to low overhead is letting the hardware do most of the work. Using 64-bit addressing, we can use aligned 4 gigabyte blocks and store all our data in higher blocks and thereby separate it naturally. We can keep the state of the memlets in additional registers that are available to us by using these wider ISAs. And we can do a whole set of additional optimizations to optimize for different corner cases. When looking at the implementation, which by the way is open source, we implemented a cross-ISA binary translator and a set of sample memlets. And the implementation is actually quite small. The binary translator, the cross-ISA binary translator, fits in only 14,000 lines of code. And each individual memlet that we implemented has roughly 100, 200 lines of code in addition to that. The binary translator component, the binary translator consists of 3 components. A specific loader component that takes care of bootstrapping the application and handling shared libraries and interactions between those. Sandbox that runs the binary translator and keeps care of translating the individual basic blocks, and the additional memlets that are then woven dynamically into the application. So now that you've seen how the system looks like, we can evaluate it using two examples. First of all, we'll look again at the unlimited watch points, and then we'll extend it into an example that is similar to Valgrind's memcheck, and we check for safe memory allocation. But let's start with the unlimited watch points. Watch points are triggered for specific memory reads and writes that are set by a debugger. And the memlet checks if a specific watch point is set for each memory access. So the only prior, we are not interested in prior versions of the memory, but only in the state of the specific memory cell. So again, we have our sample code from the beginning, where we have our simple add long instruction, and we run it through the binary translator. But this time we see that when we look at the problems that we identified in the beginning, they can be solved in a nice way. First of all, we have additional registers available. So we can just use one of the additional registers that's available, and we just use, for example, R8 to store the target address. And the memlets can use, in the current configuration, up to 4 individual registers. The second part is we can just store the shadow data that we have at a specific offset, at a 4 GB offset higher up in the memory space, and thereby access that additional data. And thereby we get very low overhead. We still execute 3 additional instructions for each memory access, but most of these instructions are very fast. And 1 additional memory access, of course. Let's look at the evaluation of this setup. We used the SPEC CPU 2006 benchmarks on a fairly modern system with 4 GB of RAMs. Of course, we ran it in the 64-bit mode, and we compare 4 different configurations against each other. The first configuration is running native 32-bit SPEC CPU on that machine to evaluate the baseline. We then look at binary translation only, the overhead of binary translation, of cross-ISA binary translation. We then look at memory tracing, which basically lists the overhead of accessing the additional shadow state for each location, and full watch points, where we set a whole set of watch points and check and do the full evaluation, not just looking up the memory, but also adding the additional handlers and taking care of these checks. This figure shows the SPEC CPU performance using the 4 different configurations I explained. We compare every benchmark against native performance and show the relative overhead. The x-axis shows the individual benchmarks. The y-axis shows performance overhead in x. On the lower right-hand side, you see the average overhead and the geometric mean. We see that overall we have very low overhead for cross-ISA binary translation. It's only about 15% on average. And for some benchmarks, like for example for LBM, we have very low overhead in general. On the other hand, if we look at other benchmarks like HMMER and Cactus ADM, for example, we see that the additional instructions that we add actually add additional performance overhead. We see that the performance overhead actually scales with the amount of memory accesses that the application executes. And in the worst case, or for the worst performing benchmark, we have roughly a 3x performance overhead, performance impact. And on average, we have less than 97% performance impact and less slowdown than that, which is fairly good performance that we see here. And we can conclude that we have low performance impact for this prototype implementation. There are still a couple of optimizations that could be done. So there's more room for improvement on top of that. If we look at the memory overhead, on the other hand, we see that, again, on the x-axis, we see the different SPEC CPU configurations. On the left-hand y-axis, we see the memory consumption in megabytes. On the right-hand y-axis, we see the percentage of memory overhead that we exhibit in total. If we look at all these different benchmarks, we see that binary translation roughly, or cross-ISO binary translation roughly adds 40 megabytes of additional memory consumption. And if we use a full watch point tracking, we actually double the memory consumption as we store 1 additional byte for each byte that the application accesses. And the memory consumption basically doubles. So we have good performance, we have good memory consumption. An obvious extension is safe memory allocation, where we check for use after free bugs and heap corruption of a running application. We are already running in a binary translator, so it's easy for us to intercept all calls to malloc and free. And the basic idea is to protect the metadata of allocated blocks, the 4 bytes before and after the block, with additional, something similar to watchpoints, and we trap into the checker if the application accesses these points. Whenever the blocks are freed, we basically write protect and read protect the whole area, and if we detect an access by the application, we see that a use after free bug occurred, and we can report that as well. And we play that game between subsequent free and use calls and can thereby offer the similar protection as memcheck. The overhead and the performance is similar to the unlimited watchpoint performance. It only has a slight additional overhead due to the additional calls to the malloc and free implementation. So we do not show the detailed graphs for that. Let's quickly look at related work. Valgrind offers very high-level transformations on machine code with some performance costs, 7x for vanilla translation. Remember, we had 11 to 15% for the binary translation and 27x for memcheck. We had less than 2x for the additional checks. On the other hand, the most perfect solution would be hardware watch points, but the hardware only supports up to 4 watch points that you can configure at one point in time. And if you use GDB and if you need more than 4 watch points, GDB basically resorts to single stepping through your application with an insane amount of overhead. If we look at other solutions, other tracing solutions, we see that they either limit the ICE that they support, for example, not executing any floating point instructions, they have high overhead, or limited flexibility in the amount of memlets that they support. Let me conclude. All in all, I presented a solution that enables lightweight, low overhead, less than 90% overhead for memory inspection for unmodified x86 applications by using additional resources that are available in modern CPUs. The memlets that we allow offer user-definable and user-configurable checks for each memory access and offer a flexible framework for memory tracing. The system is open source. We released the sources that we use for our benchmarks, and the current version is at the GitHub page. We are looking into additional applications and use cases for additional memlets. So if you want to use the system, it's free to use, and we're happy to continue with that. With that, I would like to conclude my talk, and I'm happy to take any questions.
Greg Stoy, Google. I wonder if you looked at address sanitizer?
Yeah.
Okay. So it's very similar in terms of memory checking, and it has similar performance overhead.
You mean the LLVM address sanitizer?
Yeah.
So you have to run the application through LLVM and compile it through LLVM?
You have to compile it with client.
So it doesn't
yes.
support the unmodified application.
Correct.
And the solution I present here supports unmodified any code that you write in any compiler that you've used.
But
and address sanitizer works on top of a compiler.
That's right.
And it's a great solution, and I really like the work that they did, of course. Yeah, thanks.
Hi, Nathan Bronson at Facebook. I was wondering how you deal with the operating system. So like, for example, mmap gives you back pointers. How do you make sure that they fit into the space that you're allowed? Or are also checking on pointers that are passed into the operating system?
Yeah. This is actually a great question. So we are executing 64-bit system calls. So we have to do a mapping to the 32-bit version. We have to ensure that we can use we stay, for example, for memmap, we stay in the lower 4 gigabytes, and we can actually enforce that and give additional details to it. or we can run the 32-bit versions for some.
Do you check the values that are passed through? Like if I asked for 8 gigabytes of memory to mmap, do you trap that?
You cannot ask for 8 gigabytes. The application is still running in, you only have 32-bit pointers as part of the application. The application assumes it's still running in a 4 gigabyte address space, right?
Okay.
And we support the regular system call interface, so the application still uses the original system calls. And in the binary translation layer, we map from the 32-bit versions to the 64-bit versions. For mmap, we just ensure that we return something in the lower 4 gigabytes. For other system calls like stat64 and so on, we have to ensure that we basically map it to the older version in the 32-bit world.
So a follow-up question to that is, do you have any impact on the ability to use vsys calls? Like, do you have to fall back to the normal syscall mechanism?
You mean the syscall instruction?
No, if you don't know the answer, then you don't have to worry about it, I think. There's a region of memory that you can use to bypass, that you can use to
you mean the mapped page for the fast system calls?
Right, for
yeah,
good time of day
that's supported, that's mapped as well.
Okay,
yeah.
thanks.